Welcome, everyone. Today, we're diving into the exciting and rapidly evolving world of nuclear energy. For decades, nuclear power has been a significant, yet sometimes controversial, part of our energy mix. But now, the landscape is changing, driven by the urgent need for cleaner, safer, and more adaptable power. Two remarkable technologies are leading this charge: small modular reactors, or SMRs, and the long-sought dream of nuclear fusion. They're quite different, but both aim for a lower carbon future. Let's first look at small modular reactors. Think of SMRs as the next generation of nuclear fission technology, the same basic principle as current plants, but smaller and smarter. These reactors typically produce 300 megawatts of electricity or less, and their key feature is modularity. Components can be built in a factory and then assembled on site. This offers some big advantages. Many SMR designs boast enhanced safety, using passive systems that rely on natural forces like gravity to cool the reactor, even if things go wrong. Their smaller size means they can be deployed in more places, including remote areas, and capacity can be added step by step as needed. Factory production also holds the promise of faster construction and lower costs, though we're still waiting to see this proven at scale. And SMRs aren't just for electricity. They can power industrial processes, create hydrogen, or even desalinate water. However, it's not all smooth sailing. Regulatory frameworks are still catching up to these new designs, and public acceptance remains a hurdle. Ensuring a strong supply chain and making them cost competitive are also key challenges. Despite this, development is moving fast. Countries like the US, Russia, China, and Canada are all pushing forward. Some SMRs are already operating, and many expect a broader rollout between 2030 and 2035. Now, let's shift gears to nuclear fusion. If SMRs are an evolution, fusion is a potential revolution. This is the process that powers the sun, where light atomic nuclei, like hydrogen isotopes, are fused together, releasing enormous amounts of energy. Unlike current fission reactors, fusion offers some truly game-changing possibilities. The fuel, deuterium from seawater, and tritium from lithium, is virtually inexhaustible. Safety is another huge plus. A runaway chain reaction simply isn't possible. If anything goes wrong, the reaction stops. While it's not zero waste, the radioactive materials produced would have much shorter half-lives than fission waste, and like fission, it produces no greenhouse gases. The catch? Achieving controlled fusion on Earth is incredibly difficult. We need to create and hold a plasma at temperatures over 100 million degrees Celsius, hotter than the sun, and maintain it long enough to get more energy out than we put in. But we're making progress. Major international projects like ITER in France are working to prove its feasibility, and recent breakthroughs, like achieving net energy gain in US experiments, are incredibly encouraging. Private investment is also surging. Still, commercial fusion power plants are likely decades away. Some optimists see the 2030s for compact reactors, but many experts think it'll be closer to the second half of this century. We still need to solve tough challenges in materials, science, and plasma control. So we have SMRs offering a nearer-term, more flexible evolution of fission technology, ready to help decarbonize in the coming decades. And then there's nuclear fusion, a long-term ambition with the potential to completely transform our energy future. The shift in nuclear energy is clear. We're moving towards a more diverse range of technologies. SMRs are an important step now, while fusion shines as a beacon for generations to come.